Okay, girls. Any questions? Any questions of the relationships?
No.
So you girls are good on that? Good. Now, as I just said earlier, that okay, yes, that a beam is okay. Well, let's change the shape of an hourglass, right? Okay. Yep. Now, what we mainly can say, that's going to yes, okay, it's okay, become it's okay, we can go, it's okay more practically. Because okay, one PCT actually is okay, may be considered as okay, small tiny crystals. The meaning can say that okay, as each crystal is going to just okay produce its own small wavelet. Okay, or these wavelets here, okay, that means okay, what they call is okay, the spherical waves. Actually, it's okay. It's not going to be spherical, it's actually going to be okay, we can say it's okay, V-shaped wave. Or rather, it's okay. This is still a V shape, although it's okay, we can say it's okay, tilted. Right, okay. And what these V-shaped waves here also are going to be called as okay, we can call them V-shaped wavelets. Where wavelets is made as okay, just referring to as okay, a small and or they can be called as okay, a hugen, or even as okay, a hugen wavelet. And the reason that we call them hugens or hugen wavelets is that it's actually going to be okay, what happens to these wavelets here or hugens here as they are transmitted. Now just consider as okay, one hugen or one huge wavelet to be as okay, one sound wave. Okay. But what we mainly can say is that okay, as your PCT is going to is okay, be considered as a group of small tiny pieces of PCTs. Where each small piece of the PCT actually is okay, will produce its own spherical wave, or what we can call it, okay, a V-shaped wavelet, or which is also going to be known as a hugen or a hugen wavelet. Okay. Where we mainly can say okay, a hugen or a hugen wavelet or a spherical wave or a V-shaped wavelet actually is going to be considered as one sound wave. Okay. Did you girls get that?
Yeah.
So what is it that we actually end up with? We can say it's okay, the PCT, but actually that's okay divided into, we can say it's okay, small tiny pieces where each piece produces its own wavelet, or known as fusion. We actually end up having as okay multiple waves, because we can say one wavelet or one fusion is going to be equal to one sound wave. So mainly as okay, as we have multiple wavelets, that will mainly mean that we have multiple fusions, or actually as okay, more correctly, multiple sound waves being produced by the PCT. So that's going to be as okay, multiple fusions or sound waves that will travel. Okay. And the reason that we call them Huygens, because okay, there was a guy, his name was Christian Huygens. And what he actually is okay, mainly is okay, explained is that how is it that, because it's okay, multiple wavelets, or what we can call as okay, multiple Huygens actually is okay, causes or leads to is okay, the beam become hourglass shaped. Okay, and okay, as what we end up with is going to be as okay, a sound beam that okay is going to narrow down, reach to its narrowest point, which we will call as okay, the focus. Now just look here, girls, as okay, we said multiple sound waves. Or we could say it's okay, multiple Huygens. Because we may say okay, one Huygen or one wave or wavelet is one sound wave, which is going to be the same as saying one Huygen. So multiple wavelets, multiple Huygens, or multiple sound waves, it means the same. Clear? Now, yes, okay, are traveling in a medium. And one thing that happened when we had multiple waves, or we could say as okay, two or more than two waves. Or which we could call, or we can call this okay, Huygens. Two or more than two Huygens, which means it's okay, well, just waves or sound waves that will lead to interference, right? Did you guys call interference?
Yes.
Right, okay. When did we have interference? When two or more than two waves or traveling in a medium, right? Okay. Okay. They will interfere. Did that make sense? Here we just call it, okay, the wavelets or waves. We refer to them as Huygens. We call it, okay, what the Huygens principle mainly as, okay, just states. Oh, let me just go to another slide first. What we mean, you can say is, okay, that Huygens principle mainly as, okay, states, mainly as, okay, what we already as, okay, learned when we talked about interference. That, okay, yes, what we now call Huygens, but what we previously called sound waves interfere. Or as, okay, will undergo as, okay, what we can call as, okay, interference. What was required? That we mainly had 2 or more than 2 Huygens, or 2 or more than 2 sound waves. Right, okay. Then they will undergo as, okay, interference. What were the 2 kind of interferences that we had? We had what we call constructor interference. Right. And we say constructor interference, that was mainly as, okay, where we could say that the waves were in phase. What did it mean to be in phase? That, okay, is where they had their, where the peak of those 2 waves were at the same time. Or we could say as, okay, if the trough of those 2 waves is, okay, were at the same time. That was what we call in phase. And what will mainly happen was constructor interference. Okay. And that will mainly mean that, okay, as these 2 waves, yes, okay, yes, okay, their amplitudes will be added up. And we, yes, okay, get a final wave, which would have been this, or it's okay, which would have been this. There, okay, the other form of, yes, okay, interference was what we called destructive interference. Clear. What was the requirement for, yes, okay, waves to, yes, okay, undergo what we call destructive interference? That was maybe because I mean it's okay that the waves were out phase. And what did it mean to be out phase? Okay, yes, that peaks and troughs were not occurring at the same time. So you could say, okay, when one wave had its peak, the other wave that might be, yes, okay, traveling here would not have its peak at the same time, but I have it at a different time. Okay, so there were different varieties of being out phase. You could say, as okay, 2 waves might be as okay, completely out phase, which will mean that okay, as when one had its peak, the other wave might have had its trough. Now, both these waves here had the same amplitude, which means okay, they were physically of the same time as okay. In that case, okay, they would cancel out one another. Okay. Or if not, yes, okay, at least if they were as okay, completely out phase, but one wave was bigger, the other one, for instance, okay, was smaller, we can mean that okay, the destructive interference was going to lead to okay, as our final wave would have been something like this. Okay. Did that make sense? So due to goals, either yes, okay, constructive interference of the two or more than two waves, which yes, okay, are hugens as we now call them. Since those hugens were in phase, they will undergo constructive interference. And actually, that's okay, produce a final wave with okay, as a greater amplitude than okay, as the component waves that were added up together. Whereas, okay, as on the other hand, as okay, these multiple wavelets as okay here at some time might have be as okay, out phase, which mainly cause that okay, yes, they will destructively as okay, interfere with one another to a greater or lesser extent, all depending upon as okay, how much out phase they were to one another. Did that make sense? And as a result of that, constructive and destructive interference based upon as okay, whether the wavelets at a specific period of time is okay, were in phase or out phase, actually was going to as okay, give the beam that our shape appearance. Oh, sorry, hourglass shape appearance. Did that make any sense? So goals had it not been for us having to study, let's say as okay, the beam of sound waves in form of yes, okay, the Huygens principle, which we are looking at okay, as in chapter 9. Had it not been for that, yes, okay, we would not have been studying yes, okay, interference in chapter 3 or 2, sorry. Right. So yes, okay, here this is mainly yes, okay, just if you look at it, a mere repetition of constructive and destructive interference. Right, okay. Then in that case, we say yes, okay, there's two or more than two sound waves. Here we just says, okay, those waves can be called wavelets or Huygens. Because what actually is okay, describe the whole concept of just okay, interference of wavelets, or what we now call Huygens, was your Huygens principle. But as a result of that, that's okay, your sound beam waves form an hour-shaped glass appearance, which we call a beam. Okay, I was going to be as okay, the main purpose of the beam is that okay, yes, that the sound waves are going to be able to just okay, focus at a certain point. Okay, for now we just talked about as okay, what we can call as okay, fixed focusing. Right, okay. Every minute says, okay, well, we had a fixed focal point per transducer. Practically, yes, okay, what we have in ultrasound is going to be, yes, okay, what we will call multiple focusing. But how that works, yes, okay, we will talk more about those details in chapter number 12. Did that make sense? Right. Or you can say, okay, no multiple focusing was going to be possible if we didn't know, yes, okay, how it actually is, okay, was possible for a system to focus at one point. Maybe me, it's okay, just said, okay, what did we need to do to, yes, okay, either increase the focal depth of a transducer or decrease the focal depth. All those, yes, okay, ideas were, okay, put together and say, yes, okay, are we able to make, okay, as an all one-in-one? Maybe, yes, okay, by different mechanisms are going to be able to, that's okay, adjust the focal depths of our transducers. So the bottom line here goes is you need to know, yes, okay, what is a spherical beam? It's just going to be, yes, okay, a V-shaped wave. Wavelet. What do we call them? They are also called Huygens wavelets. Clear? Now, when we say wavelet, that means, yes, okay, it just means smaller waves. Waves which are going to be, yes, okay, smaller in size. But mainly because, yes, okay, the PCT produces multiple wavelets. That's going to be, yes, okay, we can say, okay, multiple sound waves. And what did we say in chapter 2? That when we have multiple sound waves being produced and traveling in a medium, those sound waves, which we now call Huygens, are either going to be in phase or out phase. When they are in phase, they are going to undergo as, okay, what we call constructive interference. When they are out phase, they are going to undergo what we call destructive interference. Okay. So that whole thing was okay at me. It's okay what the Huygens principle talk about. So the next thing is, okay, what does the Huygens principle talk about or deal with? Interference. Right, okay. And what kind of interferences did we have? Constructive, that we add up the amplitudes of our waves. But the requirement for that is that those waves or wavelets, or as we call them here, spherical waves or Huygens, have to be in phase. Or they can undergo, yes, okay, destructive interference. What was the requirement for that? Okay, the main thing was that, okay, yes, that those wavelets, waves or sound waves, or as we now call them, it's okay, Huygens, were out phase. Okay, and what did you get from destructive interference? That's okay, wavelets with lower amplitude or smaller amplitudes than the components waves. And as a result, that's okay, positive, that's okay, constructive interference and destructive interference of your wavelets, because at some point of time they may be in phase, at some point of time they may be out phase, causes, yes, okay, the formation of a sound beam. What did we say a sound beam was? It narrows down to its narrowest point, which we call the focus. This zone was called the near zone. Then it spreads out after the focus. What do we call that zone? We call that the far zone. Right, okay. What did we have at the focus? Highest intensity of the beam. What would that highest intensity mean? That the wavelets at that point, the waves at that point will have the greatest amplitude. What makes them have the greatest amplitude? That will be the point where they are in phase. Did that make sense? Okay.
Yes.
Not directly mentioned in the book, or at least not here. Or you can always, okay, relate it to, yes, okay, what we already have talked about. Did you guys get that?
Yes.
Yes.
Yeah.
So yes, okay, things mentioned, yes, okay, in its own way, yes, okay, at different places in the book. You link it together. So if you're able to do that, yes, okay, no question is difficult to answer. Okay? Any questions, girls? Any questions?
No.
Good. So practically, yes, okay, as far as the theory of chapter 9 is concerned, we are done. Right? Right, girls? Did you girls receive an email last night?
Yes.
Good. So should we include chapter 9 on the quiz?
No.
And that's why I said from day one, once I announce the chapters that are going to be on a quiz, even if you complete another chapter and another chapter and another chapter in the meantime, doesn't mean that, okay, I'm going to just, okay, put those on the quizzes. And because I'm willing to eat this slipper here, if somebody can prove that I didn't, or I haven't already mentioned that at least 5 times within the last week and a half, that these are going to be, as okay, the 3 chapters on your quiz. So, okay, girlies. Now, on page 143 and 144, we have, yes, okay, a total of how many questions? 9 questions. Yeah. Let's just, yes, okay, see if we can answer these questions here together. And okay, let's play around with the question to see, yes, okay, how some of the other answers, options, yes, okay, were had made sense. Okay, girls? So any questions about the Huygens principle? It mainly is, okay, just deals with interference. What 2 interferences did we had? We had constructive. That means that's okay, we mean it's okay, just add up the waves. Amplitudes or so on, so on, so. To get, okay, a final wave with a greater amplitude. We made, okay, that part of the beam is okay, it will have a greater intensity, greater power, and so on, so. Oh, yes, okay, destructive, which is mean, that's okay, going to mean that, okay, we may subtract the amplitudes of the beams from one another, yes, okay, end up with a smaller wave or no wave at all. Okay, girls. So we are on page 143. And we are looking at the first question. So again, yes, okay, what does it read? The frequency of a transducers does not change. So we can mean it says, okay, that the frequency of the transducer, we can say, okay, it remains constant. So we can say, okay, if it was, let's say it's okay, 6 megahertz, it is continued to remain 6 megahertz. Now, if the diameter of the piezoelectrical crystal increases, what happens to the near zone length? If you say, okay, yes, yes, okay, increase the PCT's diameter. Right, okay, which means you can say, okay, that we might have started off at, okay, let's say it's okay, 3 millimeters. But as okay, we increase it to, let's say, 6 millimeters. Now, what they mean is, okay, just ask you is what's happening to the near zone length. Which we also already said, okay, as well, just another way of saying it's okay. The focal depth or focal length. And we know that, okay, they are going to be as okay, directly proportional to both the frequency and the diameter. So mainly because, okay, we increase the diameter of the PCT. That is going to cause us, okay, the focal length or focal depth or near zone length to increase. Did that make sense?
Yes.
Or we could say as, okay, another way of wording that is that, okay, as it will focus at a greater depth. Right, okay. These numbers I made is okay, just for in, just to have something to refer to. You don't need to do that, but like, okay. Okay. But mainly as okay, it's all a matter of okay, as your relationships. Did that make sense, girls?
Yes.
Good. Question number 2. Now the frequency of a transducer does not change. So again, it's okay. We can say it's okay. The frequency is okay, remains the same. We can say it's okay. It was 6 megahertz. It keeps on remaining at 6 megahertz. Here. Okay, if the diameter of the new piezoelectrical material increases, okay, what happens to the beam diameter in the far zone? So what actually happens now is that, okay, as the, because it's okay, the diameter of the PCT increases. So because it's okay, we might have started, okay, as at 3 millimeters, we may as okay, increase that to 6 millimeters. But that's okay, what they mainly is okay, just ask us here is okay, what happens to the beam's diameter in the far zone. Clear? Now, in this instance, yes, okay, we kept the frequency, or we kept the, frequency as okay, unchanged. But that's not going to have much of an effect on, it's okay, the divergence of the beam. I mean, that's okay because we increased the diameter. Now we know in this, okay, know that, okay, as diameter was going to be, okay, inversely proportional to the beam divergence. So it's okay, the beam is going to be less diverging in the far zone. Is that clear?
Yes.
Right, okay. And as this here is okay, may be worded once we're done with chapter 10, sorry, is that less divergence in far zone will mean is okay, mean that we will okay, improve or have okay as an improved lateral resolution in the far zone. Okay. So that's okay. The same question can be asked, but that's okay when they may ask, okay, what happens to the lateral resolution in the far zone? It will improve. But mainly because, okay, the beam remains less divergent in the far zone. Okay. So that's okay, that's chapter 10. Question number 9. No, not 9, sorry. Okay, but again, that's okay, you can just say, okay, it's all about the relationship. Whereas, okay, they went opposite and said, well, okay, we had a 6 millimeter crystal, but it's okay, we reduced the diameter of the crystal to, it's okay, 3 millimeters. Then we will actually have had, okay, as that means, okay, that we decrease the diameter, that may decrease in the diameter actually will cause that there will be a greater beam divergence in the far zone. Or as we actually can say, okay, this greater beam divergence in the far zone mainly will mean that it will be a degraded lateral resolution in far zone. Again, yes, okay, lateral resolution, chapter 12, not 10, sorry. Okay, but just informing you guys, that's okay, what may be coming up. Question number 3. The frequency of a transducer does not change. So again, it's okay that the frequency is going to remain the frequency. Or does not change, we can say, okay, we started off at 10 megahertz. We continue at 10 megahertz. Did that make sense? Now, if the diameter of the new, okay, yes, okay. If the diameter of the new piezoelectrical crystal increases, now it means that way that we, okay, yes, diameter of PCC is increased. We can say, okay, here we had 4 millimeters, we may increase it to 8 millimeters. Now the question that they ask us here is, okay, what happens to the wavelength? Now, girls, Please, 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 please be watchful. First of all, yes, okay, it talks about the diameter. Had this been thickness rather than diameter, then okay, the thickness of the PCT changes, then the wavelength had changed. But here it's okay, they do not talk about the thickness, they talk about the diameter. Clear? So yes, okay, here practically yes, okay, it is not going to change. Another reason that okay, yes, your diameter, the wavelength doesn't change is because your frequencies remain the same. Did that make sense? So had they said that, okay, yes, that there was a change in the frequency, let's say it's okay, a decrease in the frequency, that we went from, let's say, okay, and decrease in frequency, we said, if we started at 10 megahertz, we might reduce it to, as okay, decrease it, we can say it's okay, just 5 megahertz. What would happen then? In that case, as okay, the frequency decreased, then we can mean says okay, that what had been okay as an increase in the wavelength. Although yes, okay, the diameter of the PCTs remain the same, because a decrease in the frequency mainly means an increase in the wavelength. Why? Because frequency and wavelength were inversely proportional. Clear? But had it here said yes, okay, thickness rather than diameter, then okay, yes, if we increase the thickness, although yes, okay, the frequencies might remain the same, that is going to okay lead to yes, okay, an increase in the wavelength. Where do we know that from? Chapter 8. Did that make sense? Yes, go, Lise. Did that make sense?
Yes, it did.
Okay, so that's why I told you girls in the beginning, yes, okay, when we talked about, I mentioned thickness of the PCT. That's different from the diameter. Okay, that's okay, since in this case, we talk about, it's okay, spherical, yes, okay, PCTs, but when we go later on, it's okay, we are going to have what we can call rectangular shaped PCT, where the height is going to be different from the width or breadth, which is going to be different from the thickness. So it was the thickness, this front to back dimension of the PCT that would affect the wavelength. Clear? Okay. So the reason here that I say it's okay, it remains the same is because, well, okay, one thing that okay is could have affected, yes, okay, your wavelength was the frequency, yes, okay, remain constant. If we change the frequency, or we said, okay, yes, okay, then that will, yes, okay, have its effect upon the wavelength. Had it said thickness rather than diameter, then yes, okay, that change in the thickness of the PCT will also, yes, okay, affect your wavelength. Question number 4. Now the frequency of a transducer does not change. Okay, so okay, says okay, frequency as okay remains the same. Whatever, you can check any frequency. Six megahertz, 6 megahertz. Clear? If the diameter of the new piezoelectrical crystal increases, what happens to the beam diameter in the near zone? So what happens is that we okay as we can say it's okay, the diameter of the PCC is going to increase. We can say it's okay from any size. 6 millimeter to, let's say it's okay, 10 millimeters. And what they mean is, okay, just ask us is what's going to happen to the beam diameter in near zone. That will increase. Just because that's okay, you can say it just for your 6 millimeter PCT. At the beginning here, it's okay, the beam would be 6 millimeters wide. If this was your 10 millimeter PCT, the beam's diameter would be 10 millimeter. So that's not really rocket science. What would determine, yes, okay, how much then the beam, yes, okay, will converge. In both cases here was going to be, yes, okay, the frequency. Or we can say, yes, okay, mainly because of this greater diameter of the beam. This beam here will have, okay, as a greater focal depth, which means that, okay, it has a greater near zone to compare to this other one here. Okay. Always okay, the frequency was the same, but mainly because it started off with a smaller beam diameter because of a smaller PCT. Is okay, it would end up having a lower focal depth, which means it will have a smaller near zone. Did that make sense?
Yes.
Good. Okay, girls. Question number 5. And this is a question that, okay, as many students have a hard time to understand. So let's look at it. We say, okay, at what location is the sound beam? Is the sound beam's diameter? Three times greater than the transducer's diameter. Now, girls, if you girls remember yesterday, what did we say? we said that, okay, as if a transducer, for instance, okay, let's just say that, okay, it has a diameter of 5 millimeters, right? So we says, okay, this would be 10 millimeters. Did that make sense? Right, okay, but they mainly says, okay, at what location of the beam? Now, when they says, okay, what location of the beam is okay, that could be as okay either in the near zone and or is okay in your far zone. Is the diameter of the beam going to be as okay 3 times greater your 10 millimeters? Now, first of all goes, the beam cannot be greater than the transducer's diameter at any point in the near zone. Because what's going to happen in the near zone is, okay, that's mean that's okay where the beam is converging. So it becomes smaller and smaller and smaller and smaller. And what we mainly said happened at the focus. That was just okay where the diameter of the beam was going to be equal to half of, yes, okay, what we had at the source, which was 10 millimeters. So half of that, that's mainly going to mean that, okay, here the beam is going to be 5 millimeters. What did we call this distance here? That was what we call the focal depth or focal length. Clear? Let us just assume that, okay, as this here, in this case is okay. We can just take any number. We can say, okay, was 5 centimeter. Now goes in the far zone, what do we have? What's going to happen to the beam? It's going to diverge out, right? Did that make sense? Now, if we took another, yes, okay, we can say it's okay, 5 centimeters into your far zone. Say this is another 5 centimeter. We can mainly says, okay, we are back at the diameter that we had at the source, which is again going to be 10 millimeters. Did that make sense?
Yeah.
Okay. Then we may says, okay, if you just say that it goes like this, we can say, okay, another 5 centimeters. And a 5 centimeter, we may say that, okay, as it went from half, as okay, from full to half, back from half to a full. Here it is, okay, may actually this okay be. This time becomes 20 centimeters in diameter. So which was going to be as okay, another 5 centimeters into the far zone. Where okay, as if we then go just okay, we can say it's okay, another 5 centimeter. It's going to go to 30 centimeter, which is 3 times the transducer's diameter. which is going to be as okay at a depth equal to 4 focal depths. How far? 1, 2, 3, 4. Did that make sense?
Yeah.
Any questions? So girls, that's okay. This is a question that most girls, that's okay, not girls, students come back with and repeatedly ask why. Had we just changed the number here and say that's okay. 2 times greater. Then our from is okay, the math that we just said here is okay. You can say it's okay at a depth of 3 focal depths. Because we started at 10, 10 became 5, 5 again became 10, and 10 became 20. Clear? Whereas it said that's okay, and we did that yesterday. And what depth is it going to be as okay? Equal to 1 focal depth, or to the diameter of the transducer, or what depth. It's okay, twice the focal depth. Because 1 from the transducer to the focus, and from the transducer from the focus to an equal distance. As you said here, is okay. The beam started off at okay at the diameter of 10 millimeters. It halved to the focus, which we say okay, we had focused at a depth of 5 centimeters. Then okay, as if it spreads out to the same degree as it converged in the near zone. It was okay, end up okay as being attaining a diameter of 10 millimeters at a depth of 5 centimeters or 10 centimeters, which is going to be as okay twice the focal depth. Because your focal depth is 5 centimeters. So twice the focal depth is going to be 10 centimeters. So at a depth of 10 centimeters, I chain the same diameter. Did that make sense? Did that make sense, girlies?
Yes.
Okay. So is anybody going to come back with this question? Okay, you may yes, okay, change around with the yes, okay, with the number here, right? Okay. But just remember, yes, okay, the beam's diameter cannot get greater than the diameter of the source in the near zone. So that greater diameter is meaning yes, okay, what you will see in the far zone. Okay, because it starts at this diameter in the near zone, it means okay, just converges. The divergence means okay, just goes on in the far zone. Question number 4, no, number 6. What is the shape of a beam created by a tiny piece of PCT? Now it says, okay, tiny piece of PCT. Okay. Now goes that tiny piece of PCT created, yes, okay, what we call a V-shaped wave. What did we call this V-shaped wave here? It was called a fusion or a wavelet. Did that make sense? So yes, okay, the magical word is the tiny piece of PCT. Lero Badero? Or
Yeah.
okay. Question number 7. Okay. Now, which of the following explains why a sound beam created by a dish-shaped crystal has an hourglass shape? Now, Bernoulli's principle, girl, that's something that we will talk about in chapter 18. Yeah, chapter 18. So that can't be it. As a matter of fact, it's okay, Bernoulli's principle is just okay as me is okay based on okay the concept of okay as conservation of law of energy. For me, it's okay taking as okay we can say it's okay the sum of energies such as kinetic energy and pressure energy, and say it's okay it remains constant, or the sum of those remains constant. Sheffield's law, no, I may know physics, but not that much. Ohm's law, well, okay, they still mention Ohm's law in chapter 18, which is not really as okay necessity because what Ohm's law is mean is okay, just the law of physics related to yes, okay, because it's okay, flow of electrical current against the resistance that it experiences. Yeah, so as okay, what we mean is okay, we'll talk about in chapter 18 is going to is okay, flow of blood related to yes, okay, the resistance that it experiences. So that's going to be yes, okay, pressure flow relationship. Oh, sorry, resistance flow relationship that we talk about. But yes, okay, then they just mention Ohm laws. Okay, the same relationship also as okay applies to electricity, which were described by as okay Dr. Ohms. So here's okay the only one that's okay that explains why is the Huygens principle. So it was as okay as the reason of the Huygens principle that okay as your beam attained that hourglass appearance. Did that make sense? Question number 8. Now, which of the following locations is the deepest? Okay, and we can make okay, since we had talked about the beam is going to be okay, the deepest location in the beam. Now let's just draw a beam and that's okay, look at each of them. And okay, this was your transducer, so we can make this as okay as we go here, as okay, that's going to be, it's okay, and increasing depth. Okay. So end of the Fresnel zone. Now what was the Fresnel zone? That was your near zone. So the end of the Fresnel zone, that's going to be as okay, we can say it's okay here, for instance. This is for your Fresnel zone. So that's going to be here. End of focal zone. Now this point here is okay, which means okay, well, end of Fresnel zone was going to be as okay, what we call the focus. Now when they say it's okay, end of focal zone. Now we might have okay as a zone around the focus, which we call as okay, the focal zone. And since they say end of focal zone, it's okay, that end of focal zone is going to be here. So that's B. End of the Fraunhofer zone. Now, if some of you don't know what the Fraunhofer zone is, that was just okay as another name for your far zone. So Fraunhofer zone actually means far zone. And we can say it's okay, the end of the far zone. Which will be here. And then we say it's okay, end of near zone. End of near zone was made as okay, just the same as what we had in the first one, which was okay as end of Fresnel zone. So A and D actually is okay, mainly mean the same. Just call under different names. Well, which of these here is the deepest one? This one here. Did that make sense? Well, okay, the same, yes, okay, option had been given, and this says, okay, which of these is going to be, yes, okay, not the deepest, but the shallowest. That would have been, okay, as either A or D, or both. Had it said, for instance, okay, let's say it's okay. The beginning of the focal zone as an option, then that would have been the shallowest. Right? Did that make any sense, girls?
It did.
Good. Let's just look at the last question here, girls. Question 9. Now, which of the following location is the most shallow? So we can make it okay, most shallow location of the beam. So let's just okay, make a beam and okay, look at each of these locations mentioned here. So beginning of the far zone. No, let's just okay, now to make a just okay, which is okay, make the beginning of the far zone. Let's just say that this here is okay, there is our focus. So this actually is okay, will be coming as okay, can also be as okay, be the beginning of far zone. Because this is where it's okay, your far zone begins. So this is okay, this is your far zone. So the beginning of the far zone is at the focus. Let's say it's okay, beginning of focal zone. Now this then becomes just okay, your focal zone. And we can mean it says okay. This point here is okay, becomes the beginning of your focal zone. Clear? We can say as okay, focal depth. Which will be this. Or the depth at which is okay, the beam focuses. And beginning of Fraunhofer zone, which is made as okay, just the same as we had here. So beginning of Fraunhofer zone or beginning of far zone is the same. But the question is still is okay, which of all these locations is okay, is the shallowest? It's the beginning of the focal zone. Did that make any sense at all?
Yeah.
Good. Three. Okay, my dear ladies. Now just take a break, and when we come back, yes, okay, we got some questions in the exam review that we can go over. Most of them is okay, will be as okay, repetition as okay, similar repetitions of okay as concepts that we already have discussed. Okay, but just so you guys that's okay, get a little practice of okay, looking at questions and okay, yes, figure out how to yes, okay, extract yes, okay, the valuable information from it. And okay, has to yes, okay, differentiate. Okay, how answers becomes true or false, or yes, okay, it will be right or wrong. Okay, girls. So should we say that see you ladies go back at 12:50? Is that a fair deal?
Yes.
Okay.
Yeah.
Okay, girls. Back, girls. Okay, girls. Does anybody still have any questions? Any questions, girls?
No.
Good. Okay. Let's just go to, let's do it this way. Page 487. And we will start off where we ended last time. From the questions about, yes, okay, the sound beams. Okay. So question number 3 or 4, which mainly says, okay, where is the region from the transducer to the smallest cross-sectional area of beam called? Now, what are they talking about? What do we call this region? It starts from the transducer and ends at the point, yes, okay, where the beam has the smallest cross-sectional diameter. So this area here is going to be called the near zone. Yeah, now just keep in mind, go that okay, as near zone would be the answer. Or that's okay, it can also be called the Fresnel zone. Clear? This area here, that'll be had to ask, okay, what do we call the area of the beam where it has the smallest cross-sectional diameter? Clear? Then option A as focus for had been is okay, the right answer. Half value thickness. Now we talked about that in chapter 6. Okay, what was the half value layer thickness? The distance at which yes, okay, the intensity of the beam reduced to half of the initial, right? Clear? Fraunhofer zone, that will mean that's okay, just have been this, which we also has okay called the far zone. So you can make okay, that would be the area of the beam that starts from yes, okay, where the beam is at its narrowest cross-sectional diameter and gets and increases. Clear? Did that make sense? So here's okay, the area of where the beam is okay, main is okay, from the transducer, that's okay, reaches to its narrowest point, that's going to be called the near zone or Fresnel zone. Did you ladies get that?
Yeah.
Now we just look at question 305. So it's okay, the area that starts from the beam's smallest diameter. Now what was the beam's smallest diameter? That's what we call the focus, right? Okay. So the area that starts, so it starts from here, from the focus, of which is the smallest diameter of the beam. Okay, yes, and extends deeper. So what do we call this area of the beam here that's going to be as okay, the R zone. Right, okay. Which we also as okay, as the as okay are given as okay, and the answer here, option is below. From buffer zone. Did that make sense? Fresnel zone, that mean is okay, what we just talked about. This area here. Okay, the distance zone, well, okay, just something that they made up. And okay, it's the depth of penetration. Well, depth of penetration, that will be all this. Pretty much, right? Okay. Did that make sense? Okay, goals. Question 306. Okay, let's see. Now, which of this following, or which of these terms have the same meaning? So the meaning is okay, gave us different names here, okay? One is far zone. And the goal is okay, 2 is near zone. Then we say it's okay, 3 is Fresnel zone. Four is focal zone. 5 is Fraunhofer zone. And 6 is lateral zone. Okay, best of luck with that one. Clear? Okay. So which here is okay? Is 1 and 2 and 3 and 4 the same? No, 1 and 2 are not the same. Because, okay, if we look at the beam, we can mainly say as, okay, whatever represents this part here would be 1, would be 3. We can say, okay, whatever represents this here. Okay, would be as, okay, your far zone and your Fraunhofer zone. We can mainly say as, okay, what may represent, we can say, okay, this area here, that's going to be as, okay, the focal zone. And 6 really is, okay, it's just something that they made up. Okay, so 1 and 2 can't mean the same. Likewise, okay, as 3 and 4 can't mean the same either. Okay, 1 and 4, does 1 and 4 mean the same? No. Right, okay. So likewise, okay, the 2 and 3, that will be the same, but it's not going to be this one because 1 and 4 doesn't represent the same. We can say, okay, 4 and 6. Well, okay, 4 and 6 mainly is okay, that was something that they made up. So right out, that's excluded right here. Even as okay, if 1 and 5 means the same. Okay, so that one is true. So we say as okay, 2 and 3, that will be the same. Just 2 is okay, different names for as okay, what we call the near zone, which was here. 1 and 5 would be the same. Just 2 different names for your far zone. Is that clear? Did you girls get that?
Yes.
Good. Now, mainly as okay, a question that we have talked about is okay, we can say okay, something that we have talked about ever since we start talking about the beam, which mainly is okay, what is the point or location where the beam reaches its smallest dimension? So if it says, okay, so this here was a beam. What do we call this point here or this location here? It goes under the name of focus or focal point. Clear? So yes, okay, that's what we have as okay. Option B says focus. Okay. Now question 308. Now we can make is okay, just stick with this one here because what they say is all of the following are true of the focus except from. Clear? So yes, okay, is it correct to say that okay, yes, your focus is at end of near zone? Yes, that's true. Is it also correct to say that okay, yes, your focus is at okay, as the beginning of the far zone? That is true as well. And again, yes, okay, goes. Is it correct to say that okay, as the focus is where the beam has the highest spatial intensity? That is true as well. Now, please keep in mind, God says, okay, the word spatial is critical. Because, okay, when we said spatial, okay, that was okay as the intensity of the, it's okay here we get in terms of space of the beam. Meaning it's okay because here it reaches to the smallest diameter. That's why it's okay, it has the highest intensity. What kind of intensity? Spatial intensity. Had it said temporal intensity, then okay, that would have been wrong. Clear? Because okay, your temporal intensity is going to be as okay in the pulse. Or we can say okay, pertaining to the pulse. Did that make sense? Okay. Option D. Is it true to say that the focus is at the start of the Fresnel zone, which is your near zone? Is this where your focus is? No. So all the three, A, B, and C, is okay, were correct as relation to your focus. Okay. B could, option C could have been wrong had it said spatial, had it said temporal peak rather than spatial peak intensity. Okay, then okay, that could have been wrong as well. Did that make sense? Did that make sense, girls?
Yeah.
Question number, okay. Now here that means, okay, there's going to be okay, a list of true and false statements based upon, yes, okay, a PCT crystal is shaped, okay, we say, okay, PCT crystal in the shape of a disc produces a continuous ultraviolet sound. Okay, so we have, okay, it's a disc-shaped PCT, and it is going to be, okay, a continuous wave. Okay. The beam is unfocused. Are the following statements true or false? Now, girls, just keep in mind here, it's okay, that it says, okay, yes, that it is unfocused, which mainly means not focused. Question 309. Mainly, it's okay, it says, the near zone is only the region where the beam diameters is smaller than the transducer. So the near zone is only the region where the diameter of the sound beam is smaller than that of the transducer. And that's false. Because that's okay, you will even have, okay, yes, a diameter of the beam, yes, okay, being smaller than the transducer unit, is okay, in the beginning of your bar zone. Clear? Question 310. The far zone is the only region where the beam exceeds the diameter, okay, the transducer's diameter. Yes, that is true. It can't be, yes, okay, greater than the beam's diameter, okay, than the transducer's diameter in the near zone. But it's okay, the farther we go in the far zone, that's okay. It will keep on diverging. So like at some point, it's okay, it may, it's okay, be equal to, it's okay, the diameter, but then it just keeps on diverging even further, and it's okay. So the far zone is the only area in a beam that's okay where it will exceed, or where the diameter of the beam actually is okay, will exceed the diameter of the transducer or your source. Okay. Question 310. No, 311, sorry. If the diameter of the sound beam is 8 millimeters. Okay, let's see. If the diameter of the sound beam is 8 millimeters at a depth equal to twice the near zone, then the PCT crystal has to be of 16 millimeters. Now, what they mainly say here is, would it be true to say that the PCT would be 16 millimeters? If the diameter, that is, of the beam is equal to twice the near zone. Now, what will be twice the near zone? Twice your focal depth. So if we say, as okay, this is your focal depth, or focal length, or focal distance. Okay, now what is it that your beam would be here? Here it will be 8 millimeters. But they ask us, is it correct to say that, okay, at a depth which is twice your focal depth, which would actually, if we say that this depth here, or this distance here was, let's say it's okay, 6 centimeters, so would it be correct to say that at a depth of another 6 centimeters, which will make this whole thing is okay, become 12 centimeters, that the diameter of the beam would have been 8 millimeters. No, that was what it was going to be at the focus. Okay, had it said that, okay, here would have been 16 millimeters, just as it was, yes, that would be correct, because now the depth that we are talking is twice the focal depth. Did that make sense?
Can you, I'm kind of lost in that.
This is pretty much, okay, the same kind of question that we had in the exercise review. Earlier, right? Okay, that says, okay, most girls comes back and say, okay, I didn't get that. Okay, if you look at, okay, it's which yeah, that was, which question was it? Question 5 on page 114. It's the same concept, but that's fine. Okay, what have they given us as data? They says, okay, the PCT, if that was 16 millimeters, right? Right?
Right.
That's what they say at the end of the question, but they says, okay, but they mean it says, okay, if the diameter of the beam is 8 millimeters at a depth equal to twice the near zone length. Where he says, okay, near zone length. What did we call that? We also call that as, okay, focal length. Or we also call that focal depth. Did that make sense?
Yeah.
Here, yes, okay, just to have any number two, yes, okay, lean up against. I say, okay, let's just assume that, okay, yes, our focal length, our focal depth, or near zone is 6 centimeters. This means, okay, just a number that I mean. You can make any number. You can say 2 centimeters, you can say 12 centimeters, it doesn't really matter. Did you get that?
Yes.
Good. So this is mainly as, okay, just a number that I came up with. Okay, because, okay, the two numbers that we have from our question is the 16 millimeters, which is, okay, as the size of the PCT. And what they mainly are asking us is the diameter of the beam going to be 8 millimeters at a depth which is twice your focal zone, a focal length, a focal depth. Okay, as a length that is going to be twice your focal length is going to be, it's okay, 12 centimeters because a focal depth was 6 centimeters. So now, at a depth where, okay, yes, or we can say, okay, at a depth which is twice your focal depth or focal length. If your focal length was 6 centimeters, so twice of that is going to be 12 centimeters, right? So
Mhm.
12 centimeters out, that's okay. The beam is going to be back at a diameter of 16 millimeters because at the focus it gets to half. Did that make sense?
Yeah.
Okay. So I will say as, okay, at the end of the focal length, is it true that the beam would be has, okay, 8 millimeters if the PCC had a diameter of 16 millimeters? Then that would have been true. But since this says, okay, why is the focal depth or focal length? That's where it says, okay, in the first half, that's okay, it reduces to half, but then it diverges out again. So it is false. Clear? Did you get that?
Yes.
Anybody who is still in doubt?
I have a question.
Yo.
So the 8 millimeter
Yeah.
is that's going to be the depth of that. So how did you get
No.
six?
Why would that be the
Huh?
depth? That's the diameter of your beam. Listen, dear. What they say is, what they ask you, is it true to say that the diameter of the beam is going to be 8 millimeters here? if your PCT was 16 millimeters. Now, how do we know that they're talking about this area here? Because they said your focal depth or focal length multiplied by 2. There I said, we just assume, or we just made up this number and said, okay, yes, it's for 6 centimeters. Clear, at a depth of twice this, which is going to yes, okay, now be yes, okay, 12 centimeters. The beam is not going to have a diameter which is going to be half of what it was at the source. It's going to be 8 millimeters here, because half of 16 is 8, right?
Yes.
But they trick you by as okay, saying as okay, twice the focal depth. Twice the focal depth is going to be as okay, the first 6 centimeters, that's your focal depth. Twice that is going to as okay, become into the flower zone. So at that depth, as okay, the beam is made as okay, going to be back at okay, as what it was in the beginning. If we're going to be as okay, 16 millimeters.
Okay, so my question, because it started at 16 and then it went to 8, and because it,
That's your focus, right?
yeah, so the focus is 8, and then from 8, it started to.
And you
spread
take
out.
another 6 centimeters. From this point on, that becomes twice your focal depth, right?
Yes. Okay, now I get it, okay.
Did that make sense?
Yeah, I was trying to figure out like how, because when it asks about the focal depth, I'm like, we don't have that number, so how can we know?
No, but that's why I said that's made as okay, just a number that I came up with.
This
And I
is a
say, yes,
trick
okay, you
question.
can put any number here. You can say, okay, I don't like the number 6. I like 3. Then okay, it's twice your focal depth. In that case, I would just have been 6. That doesn't really matter. You can put any number as the focal depth here.
Because we know that the
Because okay, as
PCT
it's going to be twice the focal depth, and what happened in that means okay, when you talk about is okay, the far zone.
Okay.
Clear? Well, yes, okay, they twisted the things around a little bit. Okay, so what the mainly says, okay, if the diameter of the beam at a depth equal to twice the near zone, no, they say near zone, which is this. Okay, which goes as okay, you go just as okay, this is going to be as okay, oh, that's okay. Your near zone, if that's 6 centimeters, 3 centimeters, it doesn't really matter. Okay, but they say it's okay, twice of that, which means it's okay. If it was 6, they're talking about okay, what's going to be the diameter of the beam at a depth of 12 centimeters. Or we said 3 centimeters was your near zone. That was going to be okay, the diameter of the beam at a distance twice that, which is going to be okay, a total of 6 centimeters. Did that make sense? Okay, so
Yeah,
if the diameter of the beam at a depth of the is twice the near zone, then the PCT has a diameter of 16 centimeters or millimeters. No. Clear? Okay. Okay. For it to, yes, okay, for the PC, so for the beam to have a diameter of 8 millimeters at what is twice the focal zone, that will mainly require the PCT also to have, okay, as a diameter of 8 millimeters. But here it says, okay, is it true that it will have, okay, as a diameter of 8 millimeters? Twice the focal zone or near zone? If the PCT had a diameter of, okay, as 16 millimeters? No, that is false. So 16 and 16, yes, okay. If that was the true number that they had given you. And the question here, yes, okay, that would have been true. 8 here, yes, okay, that would have been true. So if it was 8 millimeters here and 8 millimeters here, then okay, yes, at the focus, your beam would have been 4 millimeters. Did that make sense?
And that's because your focus is half it, right?
Exactly. And the mean is okay, says okay, the distance at which that's okay, the mean focus is, that's what they call it, okay, the near zone. Which means okay, that's going to be okay, the same as okay, your focal depth. If your near zone is okay from start to beginning, this is the start of your focal zone. This is the end of your focal zone. Or near zone, sorry. If this distance here is okay, was 6 centimeters, that's also going to be okay, the depth at which your beam focuses, because it reaches to its narrowest. Did that make sense?
Yes.
Good. We can go on to the next question then. So 312. So again, this is okay, now if the acoustic diameter of a beam produced by a crystal at 8 centimeters, or let's say, if the diameter of an acoustic beam produced by a crystal is 8 millimeters at a depth twice the near zone, then okay, yes, the PCT crystal has a diameter of 8 millimeters. And what I just said here, then that becomes true. Because what they say is okay, that if the PCT's diameter was 8 millimeters, is the beam then going to have a diameter of 8 millimeters at a depth which is twice the focal zone? Yes. Because at the focus in that case, that's okay, would that be 4 millimeters? Clear? So this and this is okay, that makes us okay true. This and this is okay, that makes true. Whereas if you go and say it's okay, this to this would be false, or this to this would be false. Did that make sense?
Wording on these questions is really confusing.
Yes, I agree. And that's why it's okay, let's just try to, it's okay, draw them out in pictures to try to figure an answer. But it's okay. It was never a deal that the wording of the questions has to be simple. Okay, but I mean, that's okay, just ask us, that's okay, what we just did. If the diameter of an acoustic beam produced by an 8 mm crystal at a depth twice the near zone. Again, it's okay to talk about, it's okay, twice the near zone. Okay, where we find that's okay. Again, that's okay said. If this was 6 centimeters, then we can say it's okay at a depth of twice the near zone. Or twice 6 centimeters, which would be as okay a total of 12 centimeters. Is this beam here again going to just okay be 8 millimeters? Yes. Why? Because okay here the focus is reduced down to 4 millimeters. Did that make sense?
Yes.
Good. Question 313. The near zone, let's see, okay. The near zone is the only region where the beam of the where the diameter of the beam decreases as the depth increases. So is it correct to say that okay, as the near zone is the only area of a beam where the diameter that we have okay as a decreasing diameter as the depth increases. So that is true because you may say, okay, as we increase in the depth, the diameter of the beam reduces, which means okay, we can say here it is greatest, then okay, here it is lesser, then here is lesser, 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 lesser. And then it ends up at okay being the smallest diameter at the greatest depth in the near zone. Did that make sense? And the exact opposite goes is going to okay apply to your far zone. That very means okay that we have an increasing diameter as the depth increases. Depth increases, and what happens? The diameter of your beam increases. Clear? Did that make sense?
Yes.
Good. Question 314. So now let's see. It's okay. If the narrowest, let me just do that one. Okay, let's see. If the narrowest diameter of a sound beam at a depth of, okay, let's see. It's okay. If the narrowest diameter of a sound beam is at a depth of 8 centimeters, then the PCT crystal diameter is going to be as okay 16 centimeters. Okay, now that one here is okay, it doesn't make any sense at all. Because what they mainly say is that the relative diameter of a beam is at 8 centimeters. That mainly means that okay, at a depth of 8 centimeters. That is going to be the point where that's going to be the depth where the beam has the narrowest diameter. And that's only going to be applicable is okay as if your PCT was 16 millimeters or 16 centimeters. That has nothing to do with that. We can say that, okay, yes. So that's false. But had it said that, okay, yes, the beam is going to be 8 centimeter at its narrowest point. If the PCT is 16 centimeters, then that becomes true.
Okay, so it will be, the focus would be 8 if the PCT was 16, not the
Exactly.
depth.
Exactly. The depth could be anything, right? Okay, it could be 8 centimeters. Okay, it could have been 80 centimeters. We really can't say because, okay, it's also going to just, okay, then depend upon us, okay, what the frequency was. But it's mainly as, okay, straightforward as, okay, pause to say that just because the PCT had a diameter of 6 centimeters or 16 centimeters, that the focal depth has to be 8 centimeters. No, the diameter of your PCT, of your beam at the point of focus is going to be 8 centimeters if your PCT was 16 centimeters. That becomes true. But that's not what they're talking about here. Clear? And the question is, okay, the main is, okay, just try to relate this distance here to this, which are, well, okay, they are not related. Well, okay, they are, but we really can't say because it's okay, it's also going to be depend upon it's okay, your frequency. Or you can't say, or you can't really say, okay, that's because a transducer has a PCT which is 16 centimeters, that the focal length is going to be 8 centimeters. So that's okay, that makes it false. But if your PCT was 16 centimeters in diameter, then your beam would have a diameter of 8 centimeters at the focus. Did that make sense?
Yes.
Good. Question 315. Now, the higher the frequency of the acoustic wave, the shorter is the wavelength, or shorter is the length of the near zone. So what the meaning says, okay, is it correct to say that, okay, as a high frequency will lead to, yes, okay, a shorter focal depth? They just, okay, has changed the word focal depth here as, okay, by, near zone. And says, okay, short. That is false because we know that focal length, focal depth or near zone is going to be as, okay, directly proportional to your frequency. So if one arrow goes up and one arrow goes down, that would mean I said, okay, that they said these two here inversely proportional to one another. They are not. So that makes it false. Did you girls get that?
Yes.
Question 316. The greater the diameter of the transducer's piezoelectrical crystal, the longer is the near zone length. So yes, okay, is it correct to say that, okay, yes, the diameter of a PCT, yes, okay, that is great. Then we will have, okay, as a greater near zone length. Or if you just, okay, can say it will be the same as, okay, it's your focal length or focal depth. That was true. Because we already know that, okay, as the diameter of the PCT is directly proportional to the focal length or focal depth. So greater PCT, greater focal length. Smaller PCT, smaller focal length. Did that make sense? Did that make sense?
Yeah.
Good. Question 317. Now, the thicker the continuous wave transducer's piezoelectrical crystal, the longer the near zone length. Now, you may say, yes, okay, that's true, which is false. And why is it false? Because they say thickness. So we can say, okay, the thickness is okay of the PCT. Really, that's okay, is not related to the focal depth. Did that make sense? Question 318. For this shape PCT crystal producing as okay continuous wave, which design will create a beam with the shallowest focus. So what they mean is okay, which has the shortest focal depth or focal length, which we as okay already know. This is mean as okay, just repetition. Okay, then we say focal length is okay, are going to be directly proportional to frequency, directly proportional to diameter. So what do we need? What are we looking for? PCT with smallest or lowest frequency and smallest diameter. So lower frequency, lower diameter. Please, 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 girls. Not thickness, okay? Okay.
Okay.
Did I make myself clear on that one? Don't confuse the diameter with thickness. Now, question 319, yes, okay, just ask the opposite. Okay. That, okay, yes, which or this shape PCT crystal producing continuous waves or continuous sound waves, which design will create a sound beam with the deepest focus. Deepest focus is going to be as okay, greater focal length. And that's just going to be as okay, the opposite. Higher frequency and greater diameter. Okay, because okay, focal length or focal depth was still just okay, directly proportional to the frequency and directly proportional to the diameter of the PCT. Is that clear? Did you guys get that?
Yes.
Yeah.
Good. Question 320. Now, two ultrasound systems are identical except from the diameter of the transducer's piezoelectrical crystal. Which system has the greatest or deepest focus? So it's okay, what do you mean by deepest focus? Mainly we mean greatest focal depth or length, right? Now, what they mainly said, okay, yes, both systems are identical. The only thing that is different is that the diameters of the PCTs or crystals are not equal. We can just say it's okay, that mainly mean that okay, since they're not equal, one may be bigger, one may have a lesser diameter. Yeah, what it means is okay, should yes, okay, get from is okay that they are identical here is that we can say the main is okay, the information that we need is that we can say okay, the frequencies are the same. So it's okay, this could be 6 megahertz, this could be 6 megahertz. 3 megahertz, it doesn't really matter. Clear? And it's say, okay, yes, with that information, yes, okay, which is going to have the greatest focal depth? The transducer, the system with the greatest PCT diameter. At the asked about is okay. Shallower focus remaining with me is okay, a shallower focal depth. That would have been this system. Did that make sense?
Yes.
Yeah. Question 321 is pretty much okay, that's the same, but where the mean is okay, just do the opposite and say, well, okay, two systems are identical, except from the frequency of the emitted pulse. So we can mean that okay, here is okay, the diameters of system A and system B is equal. They are identical. Okay. Okay. Except from the frequency, which means okay, as the frequencies of system A is not going to be equal to that of system B. We can mean it as okay. This could be 6 megahertz. This could be as okay, let's say it's okay, 3 megahertz, for instance. And what they mean is okay, just ask us here is which has the deepest focus. So still asking, okay, which will have these two systems will have the deepest focus, which may mean greatest focal depth. And that would be the system with the greatest frequency. Did that make sense? That they are giving us, okay, same data, or okay, not really data, but the same information, but asked us which will have had, okay, as the shallowest focus, or as, okay, the lowest focal depth, that would have been the system here. The one with the lower frequency. Because the focal depth was directly proportional to frequency. Which was the only factor that, okay, will be determined here, because it's, okay, the diameter of the PCCs were the same. Okay, they could have been as, okay, 3 and 3 millimeters, whatever. Did that make sense, girls?
Yeah.
Which question 322. Now sound wave, okay, that's as sound travels deeply into the far zone, the beam diverges or spreads out. Good. Okay, now I mean it's okay, just okay. You mean I can say that, okay, as the sound wave, yes, okay, travels deep into the far zone. Now this is your far zone. We know that the beam diverges or spread out, right? Clear? Now, okay. Which of the following is, okay, will result in minimum divergence of the beam in the far zone? So they mean as, okay, says, okay, what's going to lead to is, okay, less divergence of the beam in the far zone. And we already know that, okay, as beam divergence is, okay, that was inversely proportional to your frequency and inversely proportional to diameter. So essentially, okay, they're asking about, okay, what will lead to least divergence of the beam. I mean that you're looking for a high frequency and great PCT diameter. So that would be the option. There's, okay, the same question, just asking the opposite, which would have been, okay, or called a greater divergence of the beam in the far zone. That would just have been, okay, as a low frequency or a low diameter of the PCT. Did that make sense?
Yes.
Good. Question 323. As sound wave travels deeper into the far zone and spreads out and or diverges, okay? Okay. We already answered that one, okay, on the previous, okay. Here. What's going to happen, okay, decrease divergence. So that's okay as your question 323. 324. Two ultrasound systems are identical, except from the pulse repetition period. Right, okay. Of the emitted pulse, which system will have the deeper focus? Okay, girls. Now, please, don't say, well, okay, pulse repetition period. Okay, as we know that, okay, that is inversely proportional to, yes, okay, your pulse repetition frequency. But this pulse repetition frequency here is, okay, is not related to frequency. So whether you have a, let's say, great pulse repetition period which means, okay, will give you as, okay, a low pulse repetition frequency. Doesn't mean that you also will have, okay, as a low frequency. Likewise, a shorter pulse repetition period. Well, okay, that will give you as, okay, a greater pulse repetition frequency. But that doesn't really mean that you will have a greater frequency. Why? Because frequency and pulse repetition frequency are not related. So in that case, as okay, whether low PRP or great PRP has nothing to do with the frequency of your transducer. Because that frequency is not related to the PRF and hence not related to the PRP as well. So it was going to be the frequency of your transducer that will determine as, okay, which system either had a great focal depth or lesser focal depth. Did that make sense? So just because you saw as, okay, the term period or whatever, it's okay, I is inversely proportional to frequency, but this PRF, but that PRF has nothing to do with your frequency. And it was going to be the frequency that determines your transducers focal depth. Now, had it said period, and not PRP, then because it says, okay, a greater period will lead to, as okay, to a lower frequency, right? That lower frequency as okay will lead to as okay a shallower or a lesser focal depth, or vice versa. Because as okay a shorter period, well, okay, that will lead to a greater frequency, and that greater frequency as okay will lead to a greater focal depth, but not your PRP or PRF. PRP and PRF is mainly as okay. These two here are going to as okay be as okay the total depth of your image. Where you can say it's okay, you can have a total depth of, let's say it's okay 6 centimeters. But you can still focus at a depth of 2 centimeters. Did that make sense? Which you may or mean as okay, you can still have a depth that's a depth of 12 centimeters of imaging and still be focusing at 2 centimeters. Very many can say, okay, these numbers here, that is going to be as okay, be related to as okay, your PRP and your PRF. Whereas this number here, at least for now, is going to be as okay, be related to your frequency and the diameter. Sinka. Hey, get down. Did that make sense?
Yeah.
Okay. Now goals. Well, okay. So tomorrow, as you can say, it's okay. Is that the last day before your quiz?
Yes.
Okay,
Yeah.
goes. we can have what you can call as okay, a review session if you girls want that.
Tomorrow?
Yeah, rather than starting off with a new chapter and bombarding you with more information, right?
Okay,
Yeah,
that sounds perfect.
Okay, now when I say review, please make it productive. There's no point of just, okay, having you girls sitting and looking at my face. Right?
right.
That's not going to make you more clever.
No,
Exactly. Okay. So when I say review, yes, okay, it's better as okay if you girls just okay ask the questions. Obvious, okay, any concept, any relationship, anything that anything you just want me to just okay, you can say it's okay, clarify or go over again. My sixth sense already know as okay what some of your questions are going to be. But yes, okay, let's see. Okay,
okay,
thank you. Well, okay, you better have some questions ready tomorrow.
yes,
Clear? Okay, otherwise that's okay. I can talk about decibels from 8 o'clock to 2 o'clock or 9 o'clock to 2 o'clock. And you'll say, well, okay, Mike, that was not what we asked for. Okay,
okay,
we got the decibels. We wanted to talk about something else. Okay, then you should have asked the questions. Okay, girls, so I will see you ladies tomorrow. Have a nice day. So today is okay as your time to is okay. Finalize your reading on the topics and say, okay, I'm still not getting this. Let me ask this. Okay, shit. Another topic, I still don't get it. Let me ask this. Okay,
okay.
good. Have fun and see you girls tomorrow. Okay,
Bye.
bye-bye, my dear.
Bye.